long time.
Yeah, I talk with him every now and again. Like, I check in every week or two, see how he's doing.
Cool.
Yeah, he's a very cool dude. She's gonna
Is he
have to
gonna
take
do
my car.
another motor build off?
I hope so.
Me too. I did one time, but it was just I didn't have enough time to make the video and edit it, so I threw something together last second. And it wasn't the greatest.
All right, I think we are live now, actually. So
Alrighty.
today is 2/2/2020. So most people can just check the description and see when the video started, anyways. But welcome everybody. Let's get into this. So I am joined today by Jeremiah with Energy Supply. He unfortunately doesn't have a video camera, which, such is life. But yeah, let's get into it. How about
We
what?
hope to get one soon.
Yeah, it's handy, that's for sure, especially things like this. But also doing like live streams for experiments. I don't know if you ever thought about doing that, but that can be a lot of fun, talking with people at the same time, and pretty distracting too. So
That would be awesome.
yeah, so
We've got some experiments coming up.
yeah, I bet. So tell everybody a little bit about yourself and like how you got started in this and all that kind of stuff.
Well, I was trying to Jeremiah Ford, of course. I live in Idaho. I've been working on this project for about a year now. I've been building stuff my whole life. Started off with just junk and learning and building experiments, reading Tesla's patents, trying to replicate his work, and eventually I got more and more help with my projects, and I moved into this, what we call our laboratory now. I moved in here about 2.5 years ago, and we started doing research with the Galt generator, and unfortunately we needed some more funding to finish the Galt generator, but we ended up.
What's that? What's the Galt generator?
It's geometrically aligned lateral toroid.
Okay.
It's got a reverse lens law effect. It takes lens law. You apply the load and it accelerates under load. Generator instead of slowing down under load, which is what
How have been the results on that thing?
They were really good.
Yeah.
We found out that we needed larger cores, and it was quite expensive to build the prototype. The magnetic field, if you oversaturate your iron cores that are transferring that magnetic field, if you oversaturate them, then you produce heat.
Yeah.
If you try to flip the magnetic field when they're oversaturated, you produce even more.
Right. You kind of have the hysteresis. You have that saturation point. Yeah.
Yep.
Well, that's cool. And then what? And then where from there? When did you start getting into the turbine stuff, the Tesla turbine?
Well, we wanted to. I was thinking about how many BTUs was actually in a fireplace, and I was like, "Holy cow! Like, there's an enormous amount of energy in a fireplace."
Yeah, that's actually really it's a good idea.
Everybody's. I mean, a lot of people, especially people who are off grid, have fireplace, and they still have to pay their electric bill, even though if they were able to utilize that heat, they could get 100,000 watts of electricity out of it. Of course, no one would ever need that much, so you just use a little bit, So I started doing some pulsing effects where I was taking steam and I was boiling it and sending it through a tube with a magnet inside, and the air coming in or the steam coming in would go through the tube, push the magnet one way through a coil that was on the outside of the tube, and the steam would enter the condenser, which was a thing of water. It was a just a container of cold water. So the steam would go inside and instantly condense, creating a shock wave pushing the magnet in the opposite direction. And I got it to oscillate really fast back and forth, but I wasn't satisfied with the amount of power I was able to get from it for the amount of heat I put in.
Yeah.
And being a big Nikola Tesla fan, I was like, okay, so what would Nikola Tesla do?
Build a turbine.
Course, yeah, his turbine. He said his turbine was his favorite invention, and if you like, there's a book called The Problem of Increasing Human Energy, where he talks about the problem isn't in the it's not an electrical problem, it's a mechanical problem. And so he worked extensively on his Tesla turbine, and so I was like, well, I need to build a Tesla turbine. So we had a little CNC machine, and we started building Tesla turbines with just blades inside.
What type of materials did you start with, like as far as the blades and outer housing?
Basically, it's been Lexan ever since.
Yeah, that makes sense. That the strongest? Is that the strongest bit of plastic you think you?
It's the strongest for the cheapest price.
Yeah.
You do have better grades, higher grades of Lexan that would be nice, but when you're prototyping, you don't want to go all out and spend a lot of money on the best of the best materials and stuff like that, because you end up needing to change something because you learned something new, and you can't just go change it if you have to spend another $4,000 or whatever, to make a new prototype.
Yeah, the cheaper you can start with, the better, so long as you keep safety and functionality in mind, right?
Yeah, and then you just build prototype after prototype, and you learn on every single one. You experiment with them for hours, and you just wonder and think about them, and you read more about the patents. I mean, I've read Tesla's patents so many times. Every single time, it seems like I learned. Every time I read one of his turbine patents or any patent, I learned something new.
Same. Especially like Colorado Springs and stuff like that. I'm really into the like wireless transmission of power and high frequency and high pressure, high voltage stuff, and
like
the Tesla coiling and all that kind of stuff. But I've also looked deeply into a lot of his other patents, including like the volvular valve and Tesla turbine and stuff like that. But it's hours of enjoyment if you're into like technical stuff, and the way he wrote is pretty technical sometimes to get a grasp of.
Wrap your head around it. And you don't understand it the first time.
Yeah.
And a lot of times people will try to replicate something that in Tesla's patents, and they'll do it, and they'll say, oh, it doesn't work because they gave up their first experiment. They didn't realize that if they had just kept going, they would have figured out how to tune the device to make it work.
Yeah, and that's really that's a big thing, is tuning. Like, you gotta keep playing with it for sure.
One of the things that we are moving on to now is nozzles that we can. Now, we've been doing a lot of tuning because we've been doing a lot of turbine prototyping, but we want to have a nozzle replacement attachment so that the turbine's basically got an open part on it that you can put in any nozzle that you want.
So just like a modular nozzle design, like you just swap out.
Yep. So you can say, okay, I've got my results from this nozzle, and I need to cut another nozzle out and test my adjustments to see where I go from. What are the temperatures? And the biggest thing I've learned is that temperature in and temperature out has a lot to do with the efficiency. The more energy you extract from your fluid, the colder it will be when it exits. So you see a lot of steam engines out there blowing out steam from the exhaust of their turbine or their piston engine, like the original steam engine, and it's a bunch of waste heat. It's a ton of energy that it took to vaporize all that water, and it's not condensed by the time it gets out.
Yeah, I think that's really interesting that you're approaching it that way too, because a lot of people just look at it like just pressure, and they're not. It's not like a holistic look of that. You know, pressure also involves heat. Like a lot of times when you have to use a was it diffusion pump or something along those lines. But to get a really deep vacuum, you have to actually get the heat out because the heat is a problem. So
and with water, water expands about 2,000 times when it boils, but under vacuum, it can expand over 10,000 times its volume.
Wow, that's really interesting.
So when it goes through that phase change from liquid to gas, the more that it expands, the more efficient you're gonna get.
Yeah, that's very, very interesting. Yeah, it's super fascinating to me because a lot of this ties into a lot of the stuff that I've been playing with. But I know that with the Tesla turbine, like a lot of let me ask, like, okay, so what about the volvular valve? Have you incorporated that into the system, or do you think that that's going to be needed? The volvular valve, like the one-way valve, the solid-state valve.
See, I've realized that on your Tesla pump, if you don't have a condenser, if you've got, then this is the exhaust of your pump. Okay. So you got your turbine, and then you got the pump that sucks the back pressure out of your turbine and throws it into ambient pressure, ambient air, which is 14 psi pushing backwards on your turbine. If you got a valve in there, a one-way valve, that ambient air will actually be turned around on itself and then pushed out. So it takes all the load off of the pump.
Let's do this. I'm going to switch to your screen because luckily we can do the screen share and break that down a little bit. So, do you have, when you say a pump, you're actually using a turbine as the pump as well, like as a two-stage? Is that what you mean, or do you have a separate pump?
Yes, the pump is ideally it should be connected directly to the shaft so that you don't have to rotate it with a motor.
Okay.
Or so you got your turbine spins your pump makes vacuum to suck the back pressure out of the turbine.
Okay.
I could put this right here. I can draw this real quick. This will just be, it's kind of hard to draw on paint, but
yeah, it's a challenge.
Okay, so you got your turbine here, you got your intake here, and you got your exhaust here, one on each side, right?
Right.
And then your exhaust of your turbine in Tesla's patent comes out the side usually.
Right.
So what you've got is you've got your turbine, your fluids coming in here under pressure, spiraling around, and coming out the exhaust.
Right. You're actually very good at paint, by the way. That's pretty impressive. Are you using a mouse?
Yep.
That's pretty impressive. I'm not gonna lie.
So what happens is you end up filling up this space with no vacuum here.
Okay.
With a bunch of back pressure from ambient air trying to enter. So ambient air. Oh, hold on.
And the valve diameters are both the same, or is the outtake larger than the intake, or vice versa?
It just depends, because once you get all that vacuum, once you're actually taking that steam and turning it into, if you're using steam, and turning it into, and taking all the energy out, it gets 1,800 times smaller. So that will reduce your back pressure too, because if it's not taking up any space, then you've got vacuum to further pull the fluids in. So just for a good, we'll do another one here. This will be the pump.
Okay.
Now you want to get rid of all your back pressure from this area. It says directly in the patent. So you've got ambient air at 14 psi pushing in this way in your exhaust, and of course that clogs it up. If you can take away this ambient pressure trying to get inside of the turbine,
it's kind of like reducing resistance in an electrical circuit, right?
So the fluid enters in and then rotates the turbine, and you get power, right?
Right.
But if in the pump, we're going to do the pump over here. Okay, so the pump is the complete opposite. Usually Tesla will have a volute shape here.
Yeah.
Which is for, in my opinion, is for propulsion. It's for flying. It replaces the propeller. But with the turbine pump combo, if you're just trying to extract energy, set for like off-grid cases, I don't know why everything's so small. It's just because I'm zoomed out and I got a bigger page. Okay, so we're just gonna simplify this and add a regular exhaust. So this pump this turbine over here is the same thing as this pump over here. The only difference is the turbine gets rotated by the fluid, and over here in the pump you rotate your blade with a motor.
Okay. So you're using electromotive force and mechanically driving the pump.
Yep.
Okay.
And then you get the opposite effect. Instead of the fluid rotating and then coming out, if you rotate it, it pulls in, rotates around, and it gives energy to the fluid and then forces it out. So you end up with a low pressure here.
Yeah.
If we rotate this disc in that direction, the discs will send the fluid out this way, and it's the opposite.
Yeah.
Of the turbine, which you put fluid in this way, and it rotates the blade.
Yeah, no, it makes sense. And you're basically making extremely low pressure in between the two.
Yes.
And that's where the vacuum. Yeah.
And one of the particular people are always like, okay, so giving to the fluid over here, isn't that going to take energy from the turbine? It does. It takes energy, but the thing is it doesn't take much. But of course, okay, so let me add here that there's a Tesla valve here.
Right.
And then this is your exhaust. Of course.
Yeah.
And ambient air can no longer easily enter the turbine.
So
ambient air can't go this way. It can if there's not a pulse, and that's one of the things about the turbine and the pump, and turbines in general, is you will get a frequency of sound, and that's back and forth movement. And when you get that back and forth movement, all the backs can't go back. They actually get turned around and sent back out the other direction.
Right.
And if they're oscillating, Tesla says they will be forced in the opposite direction, twice the speed that they came in, which is really weird.
That is strange. Huh,
So,
that's fascinating. So set it. Actually, could you pull up your YouTube channel and go over, because I saw the cold steam experiment. I think you're already on it. Yeah, that was it.
yep.
Can you full screen that and like break it down a little bit, like as far as the vacuum that you're pulling, and then it looks to me like the ambient air is, you have an actual chiller in a sense outside. Is that correct?
We've got a chiller outside. It's a cold. It's what we call the condenser.
Huh.
So it's under vacuum. We've sucked all the ambient air out, and then we hooked it up to this glass jar here full of water. You see that water under that low pressure wants to boil even below its normal boiling point.
Yeah.
So check this out. We filled up that water out of hot water from our sink.
Okay, so the water's like warm essentially.
It's about 95 degrees, yeah.
Okay. And then you pull the vacuum on it.
Yep.
using just like a diaphragm pump, it looks like, so nothing too.
Yeah, the pump, you only have to pump it once, because once it gets to the cold side, it condenses and no longer takes up any space, so it can never fill up your condenser.
Huh.
Too cold.
That's interesting.
That's what the turbine's for. The turbine is for replacing, or the pump. The pump is for replacing that condenser tank, because it draws its own vacuum.
Huh.
So check. Oh, this is.
Once YouTube decides to load.
Our internet seems to be. It's okay. Just change it to 420. But okay, so notice I opened the valve.
Mm-hmm.
And then it's subjected to vacuum. And
Right.
bam, we get rapid boiling of water below its boiling point.
Right.
So notice we're at 25, 26 inches of mercury.
Mm-hmm.
We can still go up to 28, 29 inches, which is way higher. With Tesla's pump, his pump's capable of doing those higher vacuum levels.
Yeah. It's interesting because it is very similar to a turbomolecular pump. If anybody's familiar with that, like it's kind of similar. It's a turbine, right? So it's very similar. So that's really fascinating.
Yeah, absolutely. Well, it's turbine and a pump, but depends on how you use it.
Yeah.
If you apply energy to the shaft of the pump, you get a pump.
Right.
Or of the turbine, you get a pump.
Right.
But if you spin the turbine with a fluid, you get a turbine.
Yeah. You get mechanical force or
mechanical energy.
Right.
Yeah.
So after you pull the vacuum, kind of lead us through the direction of flow and all that kind of stuff, and
Okay.
and what's going on.
So this is the reason I'm doing this in paint. The reason I'm doing this like this, where we've got this part here and this part here. Ideally, these should be sandwiched on top of each other.
Okay, like side by side, or
this would be right on the same shaft as this.
yeah.
Right? So we're just doing it like this so it's easy to see.
Yeah.
So ideally what you want is you want to transfer this rotational energy over here. You want to transfer this rotational energy from your fluid into rotating your pump.
Right.
So that your pump accelerates the fluid, throws it out the exhaust.
And they're connected to the same mechanical prime mover.
Exactly. And so the efficiency of your energy transfer is extremely important.
Yeah,
and that's why if it's on the same shaft, it's so good. I mean, it's so much easier.
Yeah.
Otherwise, you have to have what I'm going to probably end up doing in the future, just for tests and stuff, is a really extremely efficient generator here and an extremely efficient motor here, which I've come up with the designs for, actually with the help of Joseph Newman, with powerful neodymium magnets these days. The only way with the powerful neodymium magnets today, you can make Newman's generator that's extremely efficient, and it doesn't have RPM limits. The problem with using iron cores is once you get that thing to a certain speed, you start losing energy with your eddy currents circulating in your iron cores, and it just robs your efficiency. That's why they're better at lower speeds. Iron cores, yes, they can transfer a lot of magnetic field at low speeds efficiently, but they can't do them at high speeds efficiently. You get rid of your iron core and you don't have to worry about RPM. You can then stick it directly on the same shaft as your turbine, and you don't have to have a belt. Problem with high speeds using belts and gears is the efficiency is robbed from the belts, and the gears rob the efficiency at high speeds. So everybody builds a Tesla turbine and they connect it with a belt to a motor. I've done it in the past. I've done the experiments, and your belt heats up or your gears heat up, and you lose all your energy through your transformation to your generator, from your motor force to your generator.
Right, from friction and yeah, from friction pretty much.
Yep.
And so that's really interesting. And so when you have a two-stage, that's basically what the two-stage is. One's a pump and one's the turbine. Is that how you're setting it up? Yeah.
Okay, so let me add. I'm gonna throw a picture in here from Tesla's turbine patent real quick. I'm already in Google. Okay. Tesla turbine patent. So I'll take this right here.
Gonna copy and paste her.
Yeah. Copy, paster, crop her up, rotator.
And stick them and duplicate.
Rotate, yeah. 90 degrees, zoom in. All right. Okay, and Tesla's actually got this in his car patent. Nobody ever knows or really knows about that. That car patent, but so you can either have your gas go in. Actually, I should get the other
image side profile.
Yeah.
Figure 1.
I used to not like paint.
It's quick and easy sometimes. Like, you don't have to go through a whole program to throw things together.
Yeah, and I did a lot of that, the photo editing and stuff when I was a kid, and I'm not very good at it anymore. I kind of stopped working on like Photoshop and all that other GIMP.
Yeah. GIMP, yeah, the open source version.
Yeah.
I play around with that stuff all the time just because it's kind of part of the my business stuff.
Yeah.
So, and that's another question. Like, do you guys have plans? What are your plans? I guess we can get into that later. Like, we'll stick with the technical stuff first, right? We'll get into the
yeah. Sounds good. Okay, so usually you've got your and that's here.
Right.
And that spirals around in the center, comes out the exhaust. The
Right.
exhaust is here. See?
Yeah.
But if
Points
you
to the bottom.
close this off, if you close this off, and then you open these up,
You make that the exhaust along the shaft.
yeah,
Yeah.
your exhaust is like that.
Straight out. 90 degrees
Yep.
from the inlet. Yeah. I've seen those designs too.
So so this would be your turbine, and this would be your pump.
Right. For the two-stage.
Now this is the intake here, and this is your exhaust.
Right.
So because they're connected to the same shaft, when your fluid rotates here, it rotates the shaft, spins the rotor and rotates the shaft. You now get this to rotate, and that's your pump. So it goes in your turbine. Let me do another color. Goes in your turbine, spirals around, comes out the exhaust, sucked into the pump, gets accelerated and thrown out the exhaust.
adding
Or
to the efficiencies of it.
of the pump.
Right, adding to the efficiency.
Yeah.
Yeah. And what about because I mean we were talking about this before we got on stream, but like harmonics for the Tesla turbine. I think that we were talking about there's a kind of a popular video where it hits a certain stage and then seems to rapidly increase in speed, and you kind of had like a theory about that. What was that?
Well, my theory is that his bearings, not his bearings, that his rotor wasn't balanced well enough, and he was hitting his critical speeds on his way up as he was accelerating. And then once it hit a certain speed, he got past the critical, or one of his criticals on the way, and it started to spin freely because there was no more friction.
Right.
From the vibration. The vibration was enormous, and then once it got past that critical, the vibration ceased, and his RPM went skyrocketing.
And that's a really practical hypothesis. I never really thought about that. I always thought like it was like a resonant chamber. You had to hit like a harmonic for it, but that might not be the case.
It's actually more simple than that. And the simplest thing about the pump, or specifically the Tesla turbine, is people are using compressed air to run it, to rotate it.
Right.
And their disk spacing are too great. They don't have enough surface area on their disk. You need really tight spacing because the viscosity of air is a lot lower than water.
Right.
So you need really tight spacing, and you need a lot of surface area in order to get any kind of torque out of it.
Have you tried running water through it at all? Any turbines you've done?
Oh yes, we're starting that now in the crafters. That's we're using warm water or hot water. We've ran it on warm water, but we're experimenting with the hot water.
Kind of like this, but the phase change of water in a way, which is really interesting. So like steam, more along the lines of like water turning to steam.
Yes, water.
Yeah.
Turning to steam under vacuum. One of the things that helps with that too is you've already got your back pressure reduced in the crafters because the entire thing's under vacuum.
Yeah, that makes sense.
Maybe I should do some drawings on the crafters. So you've got your container here. And this is your warm side.
Hyde asks what's like the best spacing? Have you found like an optimal spacing for the cold steam experiments? Is it less than air or more than air, or as far as the spacing goes?
It's if everybody would use what they're using air on for cold steam, mostly they would need to just decrease the spacing between their discs just a little bit. You also don't want real thick discs. It does make a little bit of challenge to get those discs spaced evenly, and that's what his MK2 rotor was for.
Okay.
He used forged discs, which are like perfectly flat.
Yeah.
No one ever does that. But he had to make a rotor that would be easier for people to construct.
Right.
Out of just everyday materials, and that's where the star washers come into play.
What about like if you had super fine spacing, if it was very, very tight, do you think that would increase the efficiency, or would there be a certain point where it would hurt the turbine?
Let me get a reference here.
Like let's say it's just like, you know, 0.2 of a millimeter or 0.1 of a millimeter between.
Well, we've got a direct quote from Tesla. I think would be kind of interesting because we're talking about for discs. So for high Vacua, and I think he used this with steam. I mean, he says it's used for all kinds of fluids, but
right.
Let's do a control find here. Okay, so this combination is especially advantageous. Oh, one. 3/64 of an inch. So he actually gives some dimension, which is something he rarely ever does.
Yeah, that's interesting.
So the modifications in details of construction on which the reference has been made consist in the employment of smaller spaces between the discs than has heretofore been the case. So with his vacuum patent, he wanted smaller spaces.
Yeah, that makes sense because that's like a turbo molecular pump's the same way. You want spacing really really tight to get to like, one molecule at a time, type of vacuum pulling. So that's what. But the machine tolerance on that would be pretty crazy. But it's just something that's interesting.
To give a practical example, I may state the spaces of 3/64 of an inch will be effective to produce very high vacua with discs of say 24 inches in diameter. Now this is dependent on the speed as well. Today we have much better alloys.
Yeah.
And so we can go higher speeds. And the fact that we can go higher speeds means that we can get more vacuum with less spacing. So it's definitely a big tuning job. Now what I'm going to build next, it's going to be for the Crafters, and it's going to be 1/64 inch gaps.
1/64? Wow.
Yes.
Because 3/64 is like a millimeter. It's a little bit above a millimeter.
Oh, well, this won't be my next prototype. I'm going to do a 32nd inch right now because that's all I got with the plastic discs.
Yeah.
But
that's to fine tolerance.
With a turbine. Yeah. So we're going to find out how fast we can a very high grade metal like aluminum. It's the strength to weight ratio that you want.
Right.
Higher strength to weight ratio. Tapering your discs will help. They have to be ground. But just to start seeing the efficiency effects, you don't have to go that far. I'm going to start selling the plastic 32nd inch turbine pump combo really soon here.
Oh, nice.
So we can get some more money to build the new turbine out of better materials. Because we've basically done all the tuning that we need to so far now, with the Lexan.
Right.
We started with the Lexan so that we could produce the prototypes without having to spend a ton of money every time we want to learn something new.
Yeah, that makes sense.
So
you're thinking of going like towards aluminum and for the rotors and the housing type of thing? Just go straight extruded aluminum?
Aluminum for the rotors and the housing. For this will be for the model that you would want to use to run your house on. But for the model turbines, we're going to make them out of Lexan. People will be able to look at them and see, okay, this is how it works, this is how it's supposed to be.
Innards.
If we buy a turbine, then it will give me an idea of what, it'll be a physical object in their hand, and they can test it. They can throw it on, it'll be a powerful turbine. We'll have an option to have the Newman generator attached to it or not attached. It'll be adaptable for the Crafters.
Nice.
And lots of testing can be done with it. It'll be the best plastic prototype that we've built so far.
Fair enough. And how much time goes into making one of those usually? It's handcrafted and everything.
When you're making a new prototype, the new prototype always takes longer.
Right.
But if you've got the same program, you're going to cut it out 100 times. You've got all your components that you need. You have them ordered. They're there. Table. It can actually be relatively quick.
Nice. Do you have a laser cutting like CNC?
No, right now we've got a CNC mill.
Okay. Or mill. Mill works.
Stepcraft Q series. It's a new one. It's more accurate than our old one. We started with a pretty basic machine to begin with.
Hey, but if it works, it's more than I got. I don't have a CNC at the moment. Just 3D printing. But yeah, that's handy to have machines like that. So how are you, like, what are kind of some of your ideas to bring it to market though? Are you gonna like just sell these prototypes to help fund more along with your GoFundMe? For those listening, they have a GoFundMe, you can check it out in the description.
Yes, that that the GoFundMe has got us pretty far. We just ran into, okay, we've got all the materials we need to make to make these models. We've got the machine, we've got the shafts, we've got magnets. We just need to cut them out now. We actually just hit the bottom of our bank account, and now we're trying to figure out whether we're start getting some wild turkeys in our backyard. Because we're running a little bit low on food. Our electric bill. That's pretty much our main concerns right now is the food and electric bill. But of course, we do want to. The more funding that we get, the faster we go.
Right.
The more videos we'll be able to put out.
So, have you thought about, like, just for your donators, like just giving them, like, you know, they're basically buying a prototype when it's ready and stuff like that. You guys.
Yeah.
Yeah, that's kind of the way you're gonna go.
Yep. I wanted to do a Kickstarter with Paul, but he's got a different design that I'm more comfortable with selling my design than Paul's.
Okay.
I'm not saying there's anything wrong with his design. He's still got to test it and everything, but just if I'm putting something on the line, it has to be something I know that I'm familiar with.
Right.
You know what I mean?
Right.
And Paul's done some pretty amazing things with his prototyping, and he's got the best MK2 rotor that I'm drooling over that I know of, probably in the world.
Made out of aluminum.
It's tapered stainless steel disc.
Stainless steel.
And they're tapered too, so he can reach some very high speeds. He just needs to get it up to speed.
Yeah.
He wants to get it up to speed to show how much vacuum it'll make.
And you were talking about that. You guys had kind of I'm not sure if Paul came up with it or if you guys were talking about it and it hit you, but about supersonic speeds and stuff, and kind of how that's a whole nother frontier.
Yeah. At supersonic speeds, things change. The physics change, especially under high vacuum. Everything changes. And it gets better. It gets exponentially better.
Because it no longer has the same. It no longer has like a back pressure to battle, right? It kind of hits a.
Yeah, it hits a point where it's just go, and the physics change, the electrical properties of the system change. I'm going more towards the cryophorus, and Paul's going more towards the open cryophorus, which is what we've showed. Do I still have it here? Where we put the turbine in between this boiler, this jar here, and the condenser outside.
Yeah.
I want to get rid of the condenser outside, but I still think we're going to need the boiler. See, what you got to realize when you're boiling that water, it's losing heat, it's losing temperature.
Right.
And you can boil water until it freezes.
Yeah, which is kind of counterintuitive. A lot of people.
Yeah. But you never want to let it freeze. If you have a heat exchanger in there, like a radiator, you will never freeze your water, because radiators can transfer so much heat from ambient air that it would never get to that point to where it can freeze. So basically, if you think of it like a internal combustion engine, say you're 20% efficient, you got 200 horsepower, you're essentially throwing out 170,000 watts of heat out your exhaust. Out your radiator.
Yeah.
Your radiator can transfer an immense amount of energy. It can take the heat out, or it can put heat in, depending on what you're doing. The internal combustion engine will make a ton of excess heat, and the turbine pump combo will make a bunch of extra cold, and you have to keep it warm to keep it running. So just the fact that so you're constantly heating up your water, and because it comes out condensed, it doesn't spray out all over the place. Yeah. You can recycle it and continue to use that water to turn your heat into energy.
That's interesting. So in practical uses, practical terms, you were talking about putting it in like a chimney flue type of thing in colder environments, put it in a chimney flue and be able to turn it that way with
Oh
the
yeah,
potential difference.
that's easy mode. That's like step one is to just make it the best, either solar system, or warming your water with solar,
Yeah.
or warming it with your stove, or even warming it the with a radiator sitting above your stove. I mean, it's like duh, you know.
Yeah.
How long have we had stoves and we still
Well,
can't
I have a
turn
theory.
it?
You know, I have a theory about a lot of this that I've talked about on the show a lot. Like, and a lot of people will think that maybe it's a conspiracy theory stuff, but it's not really the case. I think it has to do with like investment. You know, if you look at it this way, like we have a social dynamic, like a social engineering, socioeconomic, you could say, where you know, in order to grow a company, manufacture it, and you know, make it, you know, product ready, you know, like assembly line stuff or whatever it may be, it needs a lot of funding for it, right? And if you're an investor, you know, you don't want to invest in something that you're not going to see a return on your investment. So that can be a problem when your energy costs are so low. You know what I mean?
I gotta tell you, we have had investors talk to us many times.
That's good.
The problem is they say, "Oh yeah, so you can't tell anyone. Don't tell anyone."
Oh yeah, NDA. They want you to sign an NDA.
Yeah, they want you to sign an NDA, and they want to hide the technology right away so they can get rich quick.
Right. Well, that's kind of what I mean. That's the other aspect of it, but they're both tied together. Like it's a scarcity mindset to control supply and demand. That's the only way you're going to be able to make money off of it. Also, like you have to get a return on your investment. So, you know, if you're making energy at like, you know, like less than pennies, but it takes, you know, a couple grand, let's say, to set up a turbine and set up a system, you know, it's going to be way more expensive up front. They're not going to see the return on their investment for, you know, 30, 40 years, and no investor wants to commit to something like that. I wouldn't think. It'd be more like a philanthropic type of
Well, that's actually the beauty of the Tesla turbine. Well, see, and what we've been doing is we've been keeping this open source. We've intentionally not gone with those people who want us to keep it quiet,
which is great.
We have been getting support from we have been getting support from all the followers, from all the people that are helping.
Right.
And so we're keeping it open source for them. We're not going for the bribes because we want the world to have it.
Right. You don't want it to be shelved, or don't want it to be locked up in red tape and bureaucracy or whatever it may be.
Yeah. And Tesla wanted it that way too. Another thing is because the system's so simple, it really won't cost that much. People invest in solar systems where they buy these, you know, they buy $10,000 worth of batteries and they're dead in 4 years.
Yeah.
If they're professionals or if they really know what they're doing, they can get them to last maybe 8 years.
Yeah, 8, 12, just if they keep it over 80% and all that kind of stuff, and really know what they're doing and don't, torch their batteries.
Yeah, but during that 8 years, they degrade in quality. They get worse and worse and worse until they're just completely done.
Right.
They're no good. So, but with this system, of course, you'd be storing your water in a big tank. We found out to take ice and boil it to its boiling point, to turn it up to its boiling point, or near room temperature water up to its boiling point. It basically, if you can extract 100% of that energy, which Tesla claims, you can get a battery. Your 1 gallon of water equals 1 big deep cycle battery.
That's interesting.
So we did the math on it, and if it's 100% efficient, like my dad's solar system, the other day we made 2 pots of coffee, and we had 6 big deep cycle batteries, and they were out of juice by the time the second pot of coffee came out. It takes a lot of energy to heat water.
Yeah.
In fact, water has special properties where it can absorb more heat energy than anything else. Even mercury being heavier can't absorb as much heat energy as water.
That's interesting.
So you've got this. And I went to Home Depot the other day, and it was like $750 for a 2,500 gallon tank.
Yeah, I mean,
That's it.
It's
ridiculous.
Yeah, the heat capacity of water, like you're saying, is like one of the best. I mean, it's one of the best mediums to transfer heat.
Yep.
But
and your solar panel only gives you a regular solar panel only gives you 20%.
Yeah.
Then you charge your batteries, and then what do you get after that? You get 60% of that 20%, which makes it like 10% or less.
Right.
I'm inefficient. This is just off the top of my head here. So you're getting these panels that can get 10% of the energy from the sun. By the time it hits your inverter loses, 10% of that, which decreases it even more. If you could just take and they've got solar panels now that are heat panels that are 99% efficient.
You mean they also take the heat?
Well, the electrical panels that you can use for electricity are 20% max, basically. But a heat panel is 90 to 100 or to 99% efficient. And then you go to store it in your water battery, and you don't lose any energy while you store it. The only energy you can lose is through your insulation. But if you heavily insulate your tank,
well, and you put it underground too, you maintain a constant temperature as well.
Absolutely, and with enough vacuum, it's possible that you could run your house off of your well water. Tesla talks about that too.
That's interesting. There's also a way where you can do passive solar too, to where you could actually make a boiler without a vacuum. That's another potential. I think I've seen at least one person do that, making like a steam turbine, using like the vacuum passive solar tubes. If you've ever seen those, like an array of those.
Yep. And it's the heat transfers so rapidly and so efficiently in a vacuum.
Yeah.
If there's water introduced, that's why it can be 99% efficient. But you don't have to have 99% efficient. You can go with 90 and build your.
Yeah, anything's better than 40% or 30%.
Yeah, you can take PEX tubing in big rolls that you can buy online, paint them black, put them in a window, put them in a box, and you've got a solar panel that's 5 times more efficient than what you can buy on the market.
And how much of that, like, just what do you think off the top of your head? How much of that, like the BTU, the transfer into joules, how much energy do you think you'd be able to extract with a Tesla turbine? Like
100%.
So it just depends on, but you'll need like a cold environment, right? I mean, to have that potential difference.
No, that's the good part about the Tesla pump. The Tesla pump can provide that vacuum so that you no longer need a condenser. And in the summertime, even in the summertime where it's hot outside, you won't have to worry about that condenser warming up.
That's super interesting. I never
Tesla said he was able to achieve enough vacuum that you could literally boil water until it freezes, but you'd never let it freeze, of course.
Yeah.
You'd constantly keep it above that temperature, above that ambient temperature.
That's interesting. Yeah, I mean, I've seen like Stirling engines, modified LTD low thermal displacers or whatever that do something similar. They're very efficient, but it would be cool. I hope you're gonna get to it someday. But it'd be cool to see that working.
Absolutely.
Yeah, it'd be cool to see that working. So are you building a business around this, or is it just you're just keeping it open source and then?
Well, we're building a business around it just so that we can provide the people who can't build it themselves.
Right.
With the technology.
Open source hardware stuff, right?
Yeah.
That's super cool.
As they let us go for, we're gonna go.
Yeah, that's exactly what I'm attempting to do, but with a longer timeline. But it's interesting because like I've been starting to play around with a vacuum in the reactor I have, and just thinking about the application, like it's really, really interesting. wrap my mind around. My mind's just spinning.
Well, if your reactor makes any extra heat energy, we can definitely take 100% of that energy, turn it into electricity.
Well, so that's kind of the thing. Is it essentially it should be making a ton of heat.
Yeah.
And then like there's some theories, a bunch of theories, but all need to be tested, of course. But like one is that there's low energy neutrinos, right? So to thermalize those in some way, using the water jacket that's around it, you know, is kind of a direction I'm poking at that hypothesis and playing with that type of thing. But it's most certainly would be right in line with this, and so I might have to purchase a unit down the line. Have to retrofit it.
Yeah.
I don't think
I'd love to see what people can do with these just the prototypes.
I don't think Lexan would hold up, but I'd have to get some.
You're gonna want a metal one, but the Lexan, just off of compressed air, I spun a 1,200 watt impeller at 20,000 RPM. And that was off of plastic and 120 psi compressed air.
Yeah, it holds up pretty well. That's pretty crazy.
Yeah. So it would be definitely, if people would order the turbine prototypes, models.
Yeah.
Prototypes, they will have something that completely unique that they can experiment with, and that will help them see exactly what they need to do to build a metal version if they want.
Do you have a timeline on that, when you're gonna set that up where people can purchase that? Do you have any, like, a roadmap, you know, how long that will take?
Well, it should be pretty dang quick here. Now we're still working on the balancing patent. Maybe we'll send some that people can balance themselves, because that would increase the time that we can get them out.
Okay.
And then we'll have the option to have it balanced.
Yeah, that's a good idea.
Shortly in the future, but we need to start building them. We need to start selling them, because if people get it's in contrast to a donation. If people get something that if they could order, you know, the turbine, and it would help us out, and they'd have something in return for it right away.
Right. That's why I set up my website, SciTech Syndicate, because that's what kind of the direction I wanted to go first. Why I'm doing research and development. I don't want to get a bunch of funding donation money, and then the experiment turns out to be a flop and a failure. Then I'm like, okay, well, I just took all these people. I'd feel terrible about that, I guess. That makes sense.
Yeah, makes sense.
But you're much.
But you know, the biggest thing that gives me the confidence,
Tesla,
is Nikola Tesla.
Yeah.
I know for a fact, 100%, that I do not understand thermodynamics as much as he did.
Yeah, he's pretty savvy. pretty savvy in those things.
He predicted cell phones, you know,
predicted a lot of things. So that's a question I ask almost everybody that comes on to this show. Like, it's kind of twofold. One is, what do you think about wireless transmission of power worldwide, and his ideas for Wardenclyffe? Do you think that would have worked, and what it would have looked like?
So here's my opinion on that is that he wasn't planning on doing it like everybody says he was planning on doing it. For instance, he made he made all kinds of different waves at different wavelengths, to the point where he was making X-rays, and you could see a perfect picture of the bones inside of his hands.
Right.
He did this stuff so well, it would blow, everyone's mind would be blown if they actually understood how much he actually understood about it.
That's what he was married to, is just his research. I mean, that's all he did. So
yeah.
Yeah.
And check this out. How far can you take a solar panel, and you're thinking about wireless electricity? Now take a laser pen and shine that laser pen, 500 feet away, 1,000 feet away, and you can still hit that solar panel.
Right.
And that's just with extreme basic, simple, random idea that just popped in my head.
Right.
I mean, I've thought about it in the past, but.
So then that would be a yay on that. He could transfer it. That's a yes.
Of course he could transfer it. He made X-rays and looked at the bones inside of his hands.
What,
You don't
so
think people? He didn't misunderstand. He didn't just go out there one day and make an experiment, make the
Right.
Tesla coil, and be like, okay, there's this radiant energy coming off the Tesla coil, so I'm gonna put another Tesla coil next to it, pick up the energy or whatever.
yeah,
You know,
he was pretty thorough and didn't usually say something for a matter of fact until he experimented a lot.
yes, exactly.
Yeah.
And he wouldn't have overlooked something so freaking simple.
Yeah.
It's so obvious to me that the way that they're trying to say that, oh, he was making radio waves and it dilutes, that's when they're spreading out. That's when the waves are spreading out.
Yeah.
My belief is that he was directing energy in a beam, which makes complete sense, because you can do the experiment with a laser pin and a little solar panel. You can transfer energy wirelessly from one side of 500 feet if you want.
Right.
So if we can just randomly come up with an experiment like that will prove that it's possible, I think that Tesla understood that too, because he experimented with a whole different range of waves and energies, including his particle beam particle accelerator that the media deemed a weapon. He didn't want it to be deemed a weapon. I bet you that was his best way of transferring energy wirelessly.
That's a good thought.
With that.
Yeah, that's fair.
Device.
That's an interesting perspective, yeah. So, what do you think stopped him? That's the second part of the question. Always leads into that. What do you think stopped him from achieving what he wanted to?
Just maybe funding. I mean, and the fact that his tower was destroyed. He built this beautiful tower, and then we're just gonna destroy it. Like, why would you destroy something, even if it wasn't what J.P. Morgan wanted? Even if there was an ulterior motive behind it, why would you destroy it? It was like this instrument that Tesla built.
Yeah, it's odd. It's very odd.
Yeah.
And then financially assassinate him too is kind of odd.
Exactly.
Yeah.
Exactly. And his dream was to help humanity. He didn't get to help humanity as much as he knew that humanity could be helped. And so that was probably depressing for him.
I 100%. Yeah. I mean, I'm not even to that level, but I have days where I feel like that. I think everybody kind of has that, like empathy. Like, it's almost like when you're young, when you're a kid, and you look around and you start to become aware of what we do to, like, let's say animals and stuff like that, and our environment, and you kind of get a sense of perspective of being human and what we do, physically on this planet can be a heavy burden sometimes. Like, what do you do about it? So I couldn't only imagine how far he took it, especially during that time, where like the industrial age was like in full force, and we had these choices what way we want to design our industry and stuff, and how we want to attach ourselves to the wheelwork of nature, like he said it. So yeah.
And the most basic thing that we have surrounding us in infinite quantities everywhere is heat, and we still can't transform it into energy efficiently. That's bull. That's
kind of goes to the socioeconomic side of things again. But that's what we're doing, right? We gotta just keep working at it and do our best and try to raise awareness of what could be possible. And what's interesting is I find in a lot of engineering, like heavy engineering circles, electrical engineering, doesn't matter the engineering, there's a lot of practicality in designing something and making something, and nothing is ever perfect, because it just depends on your parameters, how you want to build something according to what you need to get done, what work you want to do, right?
Exactly. And I've got an example of that. When I first started with the Cryophorus, I tested it the first time.
Yeah.
And everyone's like, oh, it didn't work, dang it. And I changed one thing in the morning. I was like, it's okay, it's gonna work. It's not that it doesn't work, it's that we did something wrong.
Yeah.
I woke up in the morning and fixed the problem, and we had a turbine going 20,000 RPM in the Cryophorus, running on warm water.
I bet that was a joyous moment. Got me excited.
And I knew it. And that's what everybody does. They get to that point and they're like, oh, it doesn't work.
Yeah, you got it. It's perseverance. Perseverance in all things. That's what it seems like life's about, is just persevering and keep on moving.
Mm-hmm.
Yeah, the interesting thing too is you kind of touched on is like the idea of there's energy all around us and how we tap into it, and then people think of the whole free energy stuff, which is really kind of it's a buzzword, but it's also in the media because of so many fake things.
People connect.
Yeah, immediately
They connect it to like, oh, free energy is overunity is
not possible. So it's laws of thermodynamics.
You can't destroy or create. You can't create or destroy energy. It exists in infinite quantities surrounding us everywhere.
And it's just the matter of how large you want to attach, like how large your system is, because there's no such thing as a closed system either. That's a common misconception in engineering even.
It's like there's no perfect vacuum.
Yeah, there's always going to be some type of particle or energy coming in.
Some type of energy getting in there.
Right.
Or particle moving.
Yeah.
Yeah.
So that's a really interesting aspect of engineering and what a lot of people think, like, oh yeah, you can't get something out of nothing. Well, yeah, but you also can't.
Well, you don't have to.
Well, you can't have nothing. That's there's always something. That's yeah. So it's a what do you call it? A dichotomy oxymoron. It's like an oxymoron. Yeah. Well, cool. Well, so if people want to go and check out your website, or where's the best link for people to learn more information about you? Just go to your YouTube, or
I would say the YouTube and the website, they've all got little bits of different information. We're getting our website together still. Not a whole lot of time to do everything,
Yeah.
So everything's kind of crude still, but we're.
What platform are you using? Are you using a CMS for? Are you coding it? Are you putting the language in yourself for the website, or WordPress?
Oh, GoDaddy.
GoDaddy. Well, as a domain, and then you're just using their services.
Their platform.
Okay.
Their services. Yeah.
Yeah. Well, if
that and our YouTube channel would definitely be good. I put a lot of updates on Facebook usually that no one will see on YouTube. We do have a patron, but of course that's another thing that we haven't been able to keep up on at the moment.
Yeah,
but
it's a lot.
Everything will get better and better. We're getting more and more help, and we definitely need some pay the electric bill and get some food this month.
Yeah, so do you have a day job and stuff?
No, I do this full time.
Oh wow, that's crazy. Yeah, then we definitely need to get you some more exposure and help you out.
Yeah.
So
I don't want to. Yeah.
What
stressful thinking about like if I have to, I'm gonna have to go like make some money real quick doing something. I mean, it's okay. I don't mind doing it, but it just means like that's that much time that will slow us down.
Right.
And the faster we go, the more people believe in us, and the more that we say the more that we do what we say we're gonna do in a certain period of time.
Yeah, build up momentum.
Yep. And the funding is what makes it all happen. It's what accelerates that process, and also, we're instead of just asking for funding, we're going to have those turbines for sale, those model turbines that people will be able to model their house model off of, and stay tuned for the updates so they can, eventually they'll be able to just take that model to their machine shop and have somebody cut it out for them, in metal.
Yeah.
In a metal version.
So do you have a CAD file and all that kind of stuff that you gonna just release, or
right now we've got we're actually on prototype 16. Which
wow.
one do you want? The old one that's better,
Are you using Fusion 360, or what CAD software are you using? CAD modeling software?
This is what I use right here, Design Spark Mechanical.
Okay. I don't think I've ever heard of that one.
I picked it up in about 3 days. I was drawing 2D drawings that I cut out.
Is it just two-dimensional, or is it? Oh no, it's three-dimensional. Yeah, 3D printing.
Three-dimensional, yeah. Can I take a quick bathroom break here?
Actually, we can wrap it up. I mean, we're getting We're like a little over an hour, so if you want, we can wrap it up.
Yeah.
Just want to let the viewers and the listeners know where like the best places for them to go to learn more about your stuff, and I linked the GoFundMe down below. But
Okay.
yeah, it's been really interesting, like super enjoyable, man. I appreciate you coming on. It's too bad we couldn't get Paul on. We can do another one of these in a month or two time and get an update, hopefully, if you guys are down for that.
Yeah, that would be great.
Excellent.
We're gonna have to talk to Paul. Of course, I can't completely speak for him, but we'll find a day where he's got some time and he can give his perspective on everything. And you know, he's been the other half of this research and development. You know.
Yeah. Is it just you two? Is it just you two working on this, or you got more help?
It's me and it's me and him. I've got a little team down here that really helps me out. Helps give me a little bit of monthly funding.
Awesome.
And yeah, there's a lot of
if you need help with marketing, I can help you a little bit with that. You know, maybe we can work out down the road. You could hook me up with with a version, a prototype, or even like a more final product.
Yeah.
I'd be down for that to help you guys out.
Absolutely. Yeah. That would be awesome.
Well, cool, man.
I'm really glad that we did this. I mean,
yeah.
I wish I could publish it on my YouTube channel.
Yeah, you can. I will. I'll download it and then I'll send it to you, and you can put it on your YouTube channel as well if you'd like.
Okay.
Yeah.
That'd be awesome.
Yeah.
But I'll give a link to your channel and my YouTube.
Yeah, that'd be sweet.
All right.
Well, cool, man. Well, thank you for doing this, and thank you everybody for listening. I'll put the links, the important links down below for his YouTube channel and the iEnergy Supply website and the GoFundMe. And yeah, I appreciate everybody asking questions and joining us. And until next time, be kind and have a great night or day, whatever it may be for you.
All right, everybody enjoy, and thanks for having me.
Yep, until next time.